look at this 11.13. We're just going to review the things we learned about the Argand diagram and then cover that last bit of section that we didn't talk about. So this will cover kind of the entire section. I don't have my iPad with me, so everything is already written. I'll just kind of be speaking and pointing using the mouse. So you'll be able to see and copy down anything. If you need to pause the video, if I'm going too quickly to write something down, just pause the video. So this section was talking all about the Argand diagram, which, if you remember, is just a representation of how we put complex numbers onto a coordinate system. So the x-axis here that you can see in this graph is the real axis, and the y-axis here is the imaginary axis. And so just a reminder, if we wanted to graph the point, for example, 2 plus 3i, we just go 2 in the real and 3 in the imaginary. And so we can kind of equate this portion of the complex number, the a portion, the a plus bi, to be the x, and the portion in front of the I, the imaginary portion or component of this number, to be the y. Right, and so we kind of figured out, if we add them together, we get this idea that it's similar to what happens with vector addition and subtraction. It just shows movement in the x and the y, right? And so if I add -2, -2, it goes from here, left 2, down 2. If I subtract -2, -2, well, then it's going to go up. Well, I guess it's going to go right 2, then up 2. Right, and just showing that that happens, right? Translation of 2 units down, 2 units left when we were adding those things. We talked about the difference between polar and rectangular form, right? So this is rectangular or Cartesian form of a complex number, whereas polar form, instead of using movement in one direction and movement in another, it will use an angle, theta, and it will use the length of the line created from the origin, which is called the modulus when we talk about complex numbers. It's very similar to the magnitude when we talked about vectors. It's calculated in the same way, which you can see here. And so in order to represent this point, x plus iy, or yi, instead of going right and up, we're instead saying, well, it rotates this angle and has a length of this line. And so some important terminology: modulus is what we call the length of this line. So the modulus of a complex number, right? Remember z being a complex number, uses this notation, and you can use that same notation in the calculator. And it's just the square root of the x component plus the square root of the y component, same as magnitude for a vector. The argument is found by finding the arctangent of y over x, the y component over the x component. In this example, right, it works. And when we talk about the argument is normally given between -180 and 180, which is what we were saying when we were kind of looking at the fact that it rotates from the x-axis in this direction or in this direction, and it's just whichever way is faster, right? So if the point was over here, right, down in quadrant 3, it wouldn't rotate this way because it would be faster to go down and have a negative angle. So that's why all of our angles are between -pi and +pi. So they either go -180, which starts here and goes like that, or +180, which starts here and goes like that. This work was just showing how we convert to this other form, right? So we're talking about this polar form, and so polar form is written like this, and it's often called the cosine I sine form, or shortened to CIS, or modulus argument form, because it shows you both the modulus, right, the length of the line created, and the argument, which is the angle created. And so we summarize the two forms here. So you have this rectangular Cartesian form, which is a plus bi. You have this polar form, which is usually written in two ways, where you have the modulus times cosine of whatever the angle is plus I sine of whatever the angle is, or it's shortened to r, and then this notation just shortens down cosine I sine, and then the angle is only written once. So these two are polar form, and this one is rectangular form. And then we went on to do some work with converting between polar and rectangular. And so we said, okay, it has modulus of 4, an argument of -2. well, let's put in our argument of -2 into the polar form, our modulus of 4, and then distributed the 4 and said, okay, well, that number evaluated in the calculator is this, and that's the A in the A plus BI, and that number evaluated in the calculator is the B, and that's the B. And so this is the number right here. This is the number in polar form, and this is the number in rectangular form. And they're exactly the same, right? There's just different representations of the same thing. And remembering that we're always in radians for complex numbers, a very important thing. Okay, so then we said, okay, well, now let's take some rectangular points, right? Some Cartesian complex numbers, and figure out, well, how do I convert them to modulus argument form, right? So it says find the modulus argument form of these complex numbers. So we looked at the first one and we said to find the modulus, it's square root of x plus square root of y, so 2 root 2, which you could write as a decimal, but we left. Then it says find the argument, so arctan of 2 over 2, which is this. And so the form written out in the long form is this one, right? That's the long polar form where you have r, the modulus, cosine of the angle, plus I sine of the angle. And then in the shortened version, that's r, that's cis, and that's the angle that exists, right? So that's the first point. This complex number goes with this z1 over here. And then we did the same thing for z2, right? Found its modulus, found its argument, and then just wrote it in cis form. And so this is generally the easier way to write it because it's less writing than this. So we have our two numbers in modulus argument form or polar form. Then it says hence find the area of the triangle. And so if we want to find the area of the triangle, it's useful to draw it. So if we draw it, our first point was approximately there, and that was using the rectangular form. It was just easier, 2 plus 2i, right 2 up 2. And then our next one is 3 minus 4i, so it goes right 3, down 4, so it's down here. So we have this triangle here, and we said, well, if I want the area of a triangle, it's 1/2 AB sine C. And so A is 2 root 2, that's the modulus of the first number. B is 5, because that's the modulus of the second number. So that's where those numbers came from. The 1/2 stays 1/2. And then to figure out the angle, right, the angle created was from the x-axis up here was the first angle. So that was the argument of the first one. So the argument of the first number was this. And then the argument of the second one was negative this number. But if I want the whole angle, I just need the positive. So we took the argument of the first, the positive argument of the second one, added them together. If you had rounded, it would have been this. If you had put in the exact values, copy and paste, it will give you exactly 7 when you calculate this in your calculator, right? So we get the area here. And so then another important thing that we figured out is how to use the calculator to do this. So if I put in, for example, this number here, 3 minus 4i. If I type that in my calculator, I type 3 minus 4, and then I is shift 2, I believe. I don't have my calculator with me, but shift 2. And then I hit enter. What will happen is the calculator will always, by default, give you the rectangular form. So if I type 3 minus 4i, I hit enter, it will just give me 3 minus 4i again. But then if I click shift multiply, which is giving you this little angle symbol here, if I do shift multiply, it will switch it to polar form. And so it will list the modulus first, it'll list the 5, then it will have a little angle symbol, and it will list what the argument is. So this is work, right? Like this work right here isn't work you really have to do because your calculator can just do it for you. We just want to understand where it's coming from. And it's better to do it using your calculator because then there's not a chance of a mistake, right? The conversion is just really fast. And so the modulus can also be found using the absolute value. So if you go into this symbol, right, you choose the absolute value symbol, you type in your complex number. So if I did absolute value of, and then inside the absolute value bars put 3 minus 4i, hit enter, it will give me 5, right? So that will find just the modulus of it. Okay, so this is the part that we hadn't gotten to yet. And really it's just showing kind of one more representation of complex numbers. And so you just need to be aware that complex numbers can also be written as exponentials. And so this is just a definition that we're not going to prove. If you want to demonstrate it yourself, you can work through Investigation 7 on page 519. It's potentially worth your time doing it today just to get a good understanding of why does this turn into this, right? Like why is this equal to that? Could be a nice thing to work through. But really, we just need to kind of know this rule, or we don't need to know it, but just accept it to understand the proof of this. And so what it's showing here is if I have cosine of pi over 2 plus I sine of pi over 2, converting that to this exponential form, which is this kind of rule that we're accepting, right? Can be proved here, but we're just accepting it for now. Then we can write it as this exponential where it's e to the I of pi over 2, or cosine I sine of pi over 2. And so what this part here is essentially doing is attempting to prove the rule that's below. And really it's some, complicated, well, it's not too complicated, but it's just basically a way of saying we have a third way to write polar coordinates. We have, if we go back for a second, we have this way is one example of writing polar coordinates. This way, which is very much related to this, right? These are almost the same. This is just shorthand for this. And then we have a third way that we can also write polar coordinates, and it will be useful for what we do next. So this was the long cosine I sine form. This is the CIS form. And then we have this other exponential form, which is, again, displaying the exact same information. And so it's just that, we can kind of see it here as well. So if you have r CIS theta, that's the same as r times cosine I sine theta. This stuff is exactly the same as what we've been doing. That's not anything new. But it's just saying you can also write it as the modulus times e to the I of whatever the argument is, right? So this theta and this r are the same as they are here, right? So if it says, well, let's write this Cartesian point in this form, well, then you can just convert it yourself, right? Like here's the work to do it, but you can also just type this number into the calculator, hit shift multiply, and it will give you the r value, which goes in front of the exponential term. Then the exponential, then usually the argument is before the I, right? When it's a variable, they put the theta after the I, but when you have an actual number, that angle, that argument is going to go here, right? Yeah, and so this is an example of how you could do it, right? This is how you could show the work to do it, but again, you could type this in the calculator, hit shift multiply, it will give you the modulus, which is in front of the angle symbol, and then it will give you the theta, which is after the angle symbol. And so then it says, okay, well, let's write this in a plus bi form, right? So we're saying, okay, here's an exponential form. This is polar, but it's exponential form. It's our third form. And this is the Cartesian form. We want to go back that way. And so we're saying, well, let's just expand this. We know this is equivalent to 3, the modulus, cosine of the argument being -2, plus I sine of the argument being -2. And then I can distribute the 3, right? So 3 goes in there, 3 goes in there. I can evaluate the thing in yellow, that's the A. I can evaluate the thing in blue, that's the B. And I get these two values for my A plus BI, right? And so here it says you can check your answers using functions in your calculator. The exponential form in your calculator will assume that you're entering the argument in radians, even when your calculator's in degrees mode, right? So that's a really important thing, that when we're doing all this complex number work, you must be in radians, right? Like it's something you need to do. You gotta understand that the complex numbers notation stuff is all in radians. All right, so make sure that you try these practice problems to make sure you understand kind of all the forms in which we can see a complex number. Kind of the most important being this last one, the exponential form, because it's what we'll do in the next section, and we'll need it to understand what we're doing in a minute. So make sure you try these practice problems. It could also be worth going and trying this investigation on page 519.